Today we'll be looking at one of the UK Chemistry Olympiad unit cell questions, which is from the paper 2010. And personally, I would say that this question is the easiest out of all the unit cell questions, because this question only require you to have the basic knowledge on how to calculate the dimensions of the unit cell, as well as the properties of the crystal lattice, such as the densities and lengths. So we will start by looking at the information given in this question. So in this question, it says that gold atoms will crystallize into this cubic arrangement, which is shown in the figure on the right. So when we look at this diagram closely, we can see that it's a face-centered cubic unit cell. So it means that all of the faces are occupied by one of the gold atoms. So this is on the face, so I'll label it face. And then we have another one at the back. So this is also mentioned in the later part of the question, which is here. The faces of the cubes pass through the center of the atoms found in the center of the faces. So it's very good if you can be calm and analyze the information given in the question first, because most likely in the UK Chemistry Olympiad question you will encounter something that you have not learned before. So if you do not have knowledge on, for example, the types of unit cell, you'll still be able to tackle this question, but you have to analyze and think about the information that they give you and how would you want to use them. So, and also so these whole texts are not very important, so you can ignore it first. And this point is quite important. So the cube is shown as a thin outline. The thicker bonds indicate which atoms are in reality in contact. Yeah, it's what I have said in my introduction to the unit cell video. These lines are actually not bonds, but it shows that the atoms are in contact with each other. So you should you should try to visualize the unit cell in the form where every atom is directly touching each other. But yeah, okay, so we will start with question A first. It tells you that the Avogadro's constant, which is how many particles are in 1 mole of the substance, and here they quote a value of 6.02 times 10 to the power of 23 particles per mole. So, and then gold has only one isotope, which has a relative mass of, so it means that 1 mole of gold here would only have a mass of 197 grams. And it also tells you that the density of the gold is 19.3 grams per cm cube. So we want to calculate the mass in grams of one gold atom. So because 1 mole has 6.02 times 10 to the power of 23 atoms of gold, So, and these atoms will have a mass of 193 grams as shown in the question. So if you want to find the mass of one atom of gold, it would just be mass of an atom would be 197 over 6.02 times 10 to the power 23. And plugging this into the calculator, I have 3.272 times 10 to the power of negative 22. So this is the mass of one gold atom. And so this statement is telling you the structure, and I've mentioned that it's a face-centered cubic structure. So you may refer to my previous video to know what is the face-centered cubic structure, but we will move on to calculate the properties of this unit cell. So here we want to count the number of atoms. And then it also reminds you to consider the fraction of each atom actually inside the unit cell. So when we look at this unit cell, right, there are 8 on the corner, 8 gold atoms on the corner, so that is 1 over 8 times 8, which is one whole atom enclosed by this unit cell. And on the faces, because it's a cube, I have 6 faces, so it will be 6 times half, which is 3 atoms. The fraction of atom at the faces is half, because if you join another unit cell next to it, you will be able to form a complete atom. So it means that each of these face only occupy half of the actual atom. So in total, I have 4 atoms. And moving on to C. And still, the question reminds you that the atoms are in contact across the diagonal of a face of the cube. So it means that, basically it means that, let's say this is the face of the cube. I have one here, I have one atom at the corner, one at the middle, which is at the face, and one at the other corner. And these should be in contact, so ignore my false diagram here. And so all the atoms, these 3 atoms are in contact with each other across the diagonal of the face of the cube. So in Ci, I want to find the edge of the unit cell, which is the distance between the center of A and B. And B in this case will be here. Yeah, so it will just be this distance. I want to, let's say I call it A. So if you watch my previous video on face-centered cubic unit cells, you'll be able to know how to calculate, but I'll just repeat my calculations here. So because all these atoms are gold atoms, so I can call it R. So I can call R the radius of this gold atom. So this is 2R, and this is R again. So using Pythagoras theorem, these are right angle triangles. A squared, which is this side, plus A squared, which is the square of length of this side, so that's 2A squared, is equal to the hypotenuse squared, which is 4R, and the entire thing squared. So my A is actually square root 8r, or you can say that it's 2 square root 2r. So now I have the answer for I, and then the volume would then be 2 square root 2 r cubed, because this is a cubic unit cell. So you would just multiply the length of the cube 3 times to get the volume. So that's 8 times 2 times square root 2 r cubed. And that's 16 square root 2 r cubed. So, and then moving on to III, it requires us to find the unit cell body diagonal, which is the distance between the center of A and C. Okay, so let me redraw the structure to make it clearer of what we need to find. So inside this cubic unit cell, we want to find the distance from this point, which is A, to C. This is the diagonal of the entire cube, and we can find this by drawing a few triangles to help us. So first I have this triangle 1 and 2. So the triangle 1 is on the base of the cube, and you can find the diagonal of this side using the Pythagoras theorem still, and so it's 2a squared equals to the diagonal squared. So my diagonal is actually 2 times square root 2 times 2r, and then square root the whole thing, which gives me oh, actually I need a square here as well. So that would just be 4r. Yeah, that's 4r, which is also the result I find from here. And then this length is 2 square root 2r. So you'll be able to find the diagonal of this unit cell by using Pythagoras theorem on triangle 2. So I have, let's say this is x, I want to find x. So x squared is 4r squared, because it's this distance, plus 2 square root 2r and the whole thing squared. So that's 16r squared plus 8r squared, which is 24r squared. So x is 2 times 6r. In part D, we are required to calculate the molar volume of gold in centimeter cube per mole. So what the molar volume means is that if I have 1 mole of gold, what would the volume of this amount of gold be? So we will still have to use the data that it provides us. So the molar, okay, so I have 1 mole of gold, and that's 197 grams, and the density of AU, the density of gold, is 19.3 grams per cm cube. So, and this actually can be written as 197 g per mole, because this is the molar mass. Actually, yeah. And then one method to solve this is to use the units, because the question wants the answer in terms of these units in centimeter cube per mole. So what you need to do is basically trying to use this and this to get a unit of cm cube per mole. So my molar volume would be just be 197 g per mole divided by 19.3 g cm negative 3. So this will give me a unit of, so let me just calculate the value really quickly. This is 10.21 cm cube. Cm cube will become, the power of cm will be positive 3 because you are dividing by cm to the power of negative 3. So this will give the unit that the question wants. And also another way to think about this question is to use logic, because I know that for 1 mole of gold, I will have a mass of 197 grams. So grams, I mean volume is mass over density. So you can use this to calculate the volume as well, to calculate the volume of 1 mole of the gold, and that will give you the molar value of the gold. So, and then moving on to part E. Part E is basically to calculate the packing efficiency, but they word it in such a way that it will be more accessible to someone who have never encountered unit cell before. So I want to calculate what fraction of the volume of the unit cell is occupied by the atoms itself. So first I need to calculate the volume of gold atoms inside the unit cell. So as I found just now, there are 4 atoms inside this unit cell. So my total volume would be 4 times 4 over 3 pi r cubed. So that's 16 over 3 pi r cubed. And then my volume of the unit cell is this one, 16 times 2 r cubed. So the fraction would just be 16 over 3 pi over 16 times square root 2. And I can simplify this to a percentage. Yes, that will give me that will give me 74.0%, and that's the fraction of the volume of the unit cell that is occupied by gold atoms. So moving on to part F, bearing in mind your answer to part E, calculate the radius of a gold atom. So we will need to use this result, which is the fraction of atoms that is actually in the unit cell, and also okay, so because I know that 1 mole of gold atoms will occupy 10.21 centimeter cube, then it means that I will need to be able to find the volume of one atom. So I can divide 10.21 cm cubed by 6.02 times 10 to the power of 23, which gives me 1.696 times 10 to the power of negative 23, and this is the volume of one gold atom. Yes, and moving on to question F, it reminds us to bear in mind our answer in part A, which basically means that inside a crystal lattice of gold, only 74% are actually the atoms. So because I want to calculate the radius of a gold atom, I would need to find the volume of a gold atom to calculate the radius. So because I know that 1 mole of gold has a volume of 10.21 cm cubed, so the volume of actual atoms would be 10.21 times 0.74, because some of the crystal lattice could be empty spaces, and that's not the atoms. So this is the actual volume of atoms, and then because this is in 1 mole, I want to find the individual atoms volume, so I will need to divide by 6.02 times 10 to the power of 23, and then this will give me the volume of one gold atom. So that's So that's 1.255 times 10 to the power of negative 23 cm cubed. The units is very important in the calculation of unit cells, so just bear in mind the units that you have used in the previous questions. And then so it means that because gold atoms are taken as spheres here, for pi r cubed would be 1.255 times 10 to the power of 23 cm cubed. So I can find my r instantly. This times 3 divided by 4. And then plugging all this into the calculator, I get r is equal to 1.44 times 10 to the power of negative 8 cm. Again, quoting the units is very important in the UK Chemistry Olympiad, because they could penalize you if you don't include the units in your final answer. So moving on to G. G is a context question, which means that it's considering the Dome of the Rock in Jerusalem, and it is a hemisphere of diameter 21 meters. Hemisphere is half of a sphere, so let me just draw it out. Okay, and this has a diameter of 21 meters. Notice that the unit here is meter, not centimeter, so you need to include a conversion of unit when you are calculating this question. So, and then one of the king of Jordan donated 80 kg of gold to cover the outside of the dome, which means that he will pave the surface area of this dome using gold. So I used yellow highlighting to show the gold here. And then so in GI, I want to calculate the average thickness in centimeter of the gold on the dome. Because it's a hemisphere, the total surface area is only half of the surface area of a circle. So I mean of a sphere. So it's 2 pi, and r is 21/2. I'll just convert it to cm. Actually, I don't need to convert to centimeters yet. So the surface area is 21 pi times 21/2 squared, and this will give me 692.72 meters squared. And looking at this, I need to pay 80 kg of gold to cover the outside. So I can calculate the volume of gold inside this 80 kilograms of gold. So in 80 kg of gold, my volume would be mass over density, and we'll use the density of 19.3 that's given to us because this gold exists in the crystal lattice, and we have to use the overall density for the crystal lattice. So that's 4145 centimeter cube, which is 4145 times 10 to the power of minus 6 meter cube. So that's, yeah, because when you convert to centimeter to meter, you need to divide by 10 to the power of 6. And to find the thickness, we have to, because volume is surface area times thickness. You can imagine it being a sheet like this. This is only the cross-sectional area of the dome. So thickness will just be volume divided by the surface area. And I get around 6 times 10 to the power of minus 6 meters. But it wants the answer in centimeter, so it will be 6 times 10 to the power of minus 4 centimeter. And then moving on to part 2 of G. Hence, calculate the average number of layers of gold atoms covering the surface of the dome. So what this means is that let's say we imagine the layers of gold. They are cubes, so I'm not sure how many of these layers are here, but the total thickness would be 6 times 10 to the power of 4 centimeter. So I can use and each of this cubic unit cell has a length of using my answer before, it has a length of 2 square root 2r, 2 square root 2r, where r is the radius of the gold atom, and as we found before, r is 1.44 times 10 to the power of minus 8 centimeter. So we can find the number of layers required now. It would just be 6 times 10 to the power of minus 4 divided by 2 square root 2, 1.44 times 10 to the power of minus 8, to find how many there's n blocks you need. How many layers do you need? So it's 1.4691.54. 14691.54. Oh, actually I didn't read the questions carefully. So it says here, it mentions here that the thickness of one layer is 1/3 of the distance A to C. So my representation of the layers of gold here is wrong, and the thickness of one layer should be 1/3 of the distance A to C, which is which I found to be 2 square root 6 times r. So I have to change my answer here a bit. So the number of layers would be the length of the thickness of the gold layer divided by 2 square root 6 times r, and that will give me and this is 1/3, and it should be 1/3 of the diagonals of the unit cell diagonal, so I have to consider that as well. So plugging all this into the calculator, I have my number of layers as 2.5 times 10 to the power of 4 layers. So this